Chapter 9, Force and Laws of Motion. Force and its effects.
We have learnt about the motion of an object along a straight line in terms of its position, velocity, and acceleration. Let us perform a few activities concerning motions of objects. Throw a ball in the upward direction. Bring a chair towards yourself. Try moving a table in your classroom to one corner of the room. Fetch a bucket full of water from a tank. Use a magnet to collect scattered pins. In the above activities, did the motion of the object start itself? That is, without any efforts? No. Some effort was required to move a stationary object. Do all motions require a cause? Yes, they do. Then what is the cause of this motion? In this chapter, let us find answers to these queries. Force and motion. We know that a body does not start moving without any efforts. Similarly, a moving body does not stop without any efforts. A ball at rest will be in the state of rest unless something makes it to move. If you hit the ball with a stick, it will start moving. We cannot stop a moving vehicle without applying brakes. You must have noticed a rolling ball stops after rolling some distance. What is the reason behind this? The reason is the friction or the resistance offered by the ground slows down the ball. Thus, a force is required to change the state of motion. Force is an interaction between two objects. We cannot see force, but we can see or feel the effects of force. For example, when a book is kept on a table, it is under the action of two forces. One, the weight of the book acting on the table, and the second, the force exerted by the table on the book, which is not visible. These two forces balance each other, and the book remains stationary. However, when a ball is hit on the ground, it bounces in an upward direction. This is the visible effect of force. You must have seen that when persons in a circus jump on a trampoline, they are thrown upwards by the net. In this case, effect of force is visible. Force can be used to make an object move faster or slower or change its direction. Force can also be used to change the shape and size of objects. We can change the shape of objects like a rubber band, spring, sponge, or a ball made of mud by applying force on it. Let us define force. Force is a physical quantity that changes or tends to change the state of rest or of uniform motion of a body in a straight line. The quantity force has a particular direction and a specific magnitude. So, to describe force, we must specify both its magnitude as well as the direction along which the force is acting. Balanced and unbalanced forces. Let us perform an activity to understand balanced and unbalanced forces. Take a wooden block. Tie two strings A and B on the opposite sides of the block. Now apply force to pull the string A to the right side. Can you move it? Yes, it can be moved towards the right. Now try and pull the string B to the left. The block can be moved towards the left. Now try pulling the block from both the sides with equal forces. Does the block move? No, it doesn't. When equal forces are applied on both the sides of the block does not move. What can we learn from this activity? When two forces acting on a body are equal in magnitude and opposite in direction, the net force acting on the body is equal to 0. Since the two forces are balanced, the body remains at rest. Similarly, when an object is kept on the table, remains at rest due to two forces acting on it, that is, the weight of the object and the reaction force by the table acting on the body are balanced. You are familiar with the game of tug of war. When both the sides apply equal force, we can say that forces are balanced. Forces that do not change the state of rest or of motion of an object are called balanced forces. An object moving with uniform velocity continues to move with uniform velocity when forces acting on the object are balanced. But an unbalanced force acting on an object brings the change in its state of motion. When a ball lying on the ground is hit with a bat, the ball is set in motion by the applied force. The force exerted by the bat on the ball is an unbalanced force. When we stop the ball in motion, we apply an unbalanced force in the opposite direction to deaccelerate the ball and bring it to rest. Thus, we can say that an unbalanced force is required to accelerate or deaccelerate the motion of an object. So, as long as an unbalanced force is applied to a body, there is a continuous change in its state of motion. What will happen if the force is removed completely when an object acquires a certain speed? Let us consider an object at rest acted by a force. The body gets accelerated as the force is acting on the body, therefore its velocity increases with time. If the force is removed, the object will continue to move with the velocity it has acquired till then.
Newton's laws of motion.
Sir Isaac Newton was a great experimental physicist as well as a great mathematician. He studied motion in detail and gave the three fundamental laws that govern the motion of objects. These are known as Newton's laws of motion. Newton was awarded a knighthood in 1705 for his work, and he became Sir Isaac Newton.
Let us now study Newton's laws of motion in detail. Newton's first law of motion.
Let us perform this activity to understand Newton's first law of motion. Put a smooth cardboard on a glass. Keep a coin on the cardboard. Flip the cardboard suddenly. What do you observe? The coin falls in the glass. Here, the coin tries to continue in the state of rest. Therefore, it falls down in the glass after removing support instead of moving with the cardboard. Every inanimate body continues in its state of rest or of uniform motion in a straight line unless an external unbalanced force acts on it. This is known as Newton's first law of motion. An object remains in its state of rest or motion if the various external forces cancel out to give zero net resultant force. Newton's first law of motion explains inertia, the inherent property of the body by virtue of which the body opposes the change in the state of the motion. It also explains the requirement of force to change the state of rest or of uniform motion of the body in a straight line.
Let us perform some activities to understand the concept of inertia.
Hit a ball and a stone of the same size with a bat. What is our experience? It is definitely easier to hit a ball than a stone. A ball is lighter than a stone of same size. The ball travels a longer distance than the stone. Now arrange the carom coins at the center of the carom board, one on top of other. Hit the coins with a fast-moving striker at the bottom. What do you observe? We see that the coin at the bottom moves out while the rest of the coins slide down. The hitting striker transfers energy to the coin at the bottom, therefore it moves out. The other coins slide down because there is no force acting on them to make them move out. Look at the rotating fan. Its blade rotates with a high frequency. Now switch off the fan. What do you observe? The blades of the fan continue to rotate for some time and then stop. In all these activities, we see that every object resists a change in its state of rest or of uniform motion. Let us see some more examples. You must have experienced a backward jerk when the bus you are traveling in suddenly starts moving from the rest position. Why does this happen? When the bus is at rest, our body is also at rest inside the bus. As the bus starts moving, the portion of our body which is in contact with the bus acquires velocity and moves with the bus. But the upper part of the body, being unaffected by any force, tries to remain at rest. As an effect, we fall back. What happens when a moving bus suddenly stops by application of brakes? When brakes are applied, the bus stops, and the lower portion of our body, which is in contact with the bus, also comes to rest. But the upper portion tries to retain the state of motion and falls forward. The tendency of a body to resist any change in state of rest or state of motion is called inertia. In the above examples, we have seen that when no external force is acting on an object at rest, it will continue to remain at rest, while a moving object will continue to be in motion with the same velocity.
Let us now understand the types of inertia.
We have defined inertia as the property by virtue of which a body resists the change in its state of rest or state of motion. We can divide inertia into three types. 1. Inertia of rest. 2. Inertia of motion. And 3. Inertia of direction. 1. Inertia of rest. The inherent property of a body by virtue of which it cannot change its position of rest is called inertia of rest. For example, when we dust a carpet, the carpet is set into motion and dust particles, due to inertia, remain in its state of rest. Thus, the dust comes out and the carpet is cleaned. When a bus starts suddenly, the passengers receive a backward jerk. The passenger's lower body in contact with the bus also start moving as the bus starts. But the upper body tries to maintain their state of rest on account of inertia. Therefore, when the bus starts moving, the passengers experience a backward jerk. A fruit falls down from a tree when the branch is shaken. This is because the branch is set in motion, but the fruit tries to stay in the state of rest. 2. Inertia of motion. The inherent property of a body by virtue of which it cannot change its state of motion is called inertia of motion. For example, when a rotating fan is switched off, it continues to rotate. The fan continues to remain in its state of motion on account of inertia. A person falls when he jumps from a moving bus. Similarly, passengers in a bus get a jerk in forward direction when the bus stops suddenly. 3. Inertia of direction. The inherent property of a body by virtue of which it cannot change its direction of motion is called inertia of direction. For example, when sharpening a knife, small hot particles of the knife fly off tangentially in the form of sparks. When a vehicle moves, the mud sticking to its wheels fly off tangentially. Hence, mudguards are provided to vehicles.
Having learnt about the types of inertia, let us now try to answer one question. Do all bodies have the same inertia? Let us find out its answer by performing an activity.
Try applying the same force to move a chair made of fiber and a bench in your classroom. What difference do you notice? We require a larger force to move the bench compared to the chair made up of fiber. Mass is also a quantitative measure of property of inertia of body. Hence, heavier objects have more inertia as compared to lighter objects. The manifestation of the property of inertia is described by Newton's first law of motion. So, it is also called as law of inertia.
Thus, all the examples of inertia are examples of Newton's first law of motion. Newton's second law of motion.
Let us perform some activities. Ask your friend to drop a tennis ball and a cork ball from the terrace. Which ball can you catch easily? It's easier to catch a tennis ball than a cork ball. Why is it so? The tennis ball has less mass than the cork ball. Here, both the balls hit your palm with same speed, but because of more mass of the cork ball and its impact is more compared to that of the tennis ball. Ask your friend to throw the tennis ball very slowly and try to catch it yourself. Now, ask him to throw the same ball with very large velocity and try to catch it. In which of the above situations can you catch the ball easily? It is easier to catch the ball that is thrown slowly than the one which is thrown with a large velocity. Why is it so? The impact produced by a ball thrown slowly is much less than that which is thrown with a large velocity. From these observations, we understand the impact or the effect of the force produced by an object depends upon both the mass and the velocity of the object. This means that there exists some property which combines mass and velocity. Newton introduced this property as momentum. Momentum P of a body of mass m moving with velocity v is defined as the product of its mass and velocity. P is equal to m into v. Momentum has both magnitude and direction. Its direction is the same as that of velocity. The SI unit for momentum is kilogram meter per second and CGS unit is gram centimeter per second. We know that the application of an unbalanced force brings about a change in the velocity of the object. The change in velocity means a change in its momentum. This means that a force also produces a change in the momentum. Newton's second law explains about the change in momentum. The rate of change of momentum is directly proportional to the impressed force and takes place in the direction in which the force acts. Let us consider a body of mass m moving with velocity u. Let a force F be acting on the body in the direction of the motion. Application of the force brings out change in the velocity. Suppose v is velocity of body after time t. The total initial momentum of a body is mu and final momentum is mv after time t. Now, the rate of change of momentum is change of momentum divided by time. That is, the rate of change of momentum is equal to change in momentum upon time, which is equal to mv minus mu upon t. On simplifying this equation, we get the rate of change of momentum is equal to m multiplied by v minus u upon t. This is equal to m into a. According to Newton's second law of motion, the rate of change in momentum is directly proportional to the force F. Rate of change of momentum is proportional to F. Therefore, ma is directly proportional to F. F is equal to k into m into a. Where k is constant of proportionality, its value is 1. In MKS system, unit of force is Newton. 1 Newton is the force which causes a mass of 1 kilogram to move with an acceleration of 1 meter per second square. It is also called 1 Newton force. 1 Newton is equal to 1 kg multiplied by 1 meter per second square. In CGS system, dyne is the unit of force. 1 dyne is the unit of force which causes a mass of 1 gram to move with an acceleration of 1 centimeter per second square. It is also called 1 dyne force. 1 dyne is equal to 1 gram multiplied by 1 centimeter per second square. Have you wondered why in a high jump athletic event the athletes are made to fall on a sand bed? This is to increase the time of the athlete's fall after making the jump. This decreases the rate of change of momentum and hence the force or the impact with the ground. Consider two objects, A and B, of masses m1 and m2 initially at rest. Let the object A be lighter than B. Suppose a fixed force is applied for a certain interval t of time on both the bodies. The lighter object, that is A, picks up greater speed v1 than the heavier object B, which moves with velocity v2. But at the end of time interval t, each object acquires the same momentum. That is, after the time interval t, we have m1 v1 is equal to m2 v2. Therefore, the same force for the same time causes the same change in momentum for different objects. It shows that force is directly proportional to change in momentum at fixed time for different objects having different masses.
In our everyday actions, the second law of motion is often seen. For example, a player on a cricket ground, while catching a fast-moving ball, pulls his hand along the direction of motion of the moving ball, due to which the momentum of ball decreases slowly so that impact of force decreases and player does not get injury on his palm. Similarly, a karate champion strikes his hand very fast on the pile of tiles or bricks so that change in momentum takes place in minimum time, due to which magnitude of force increases. Let us now solve some numerical problems on what we have learned.
1. Calculate the momentum of a field gun of mass 500 kilograms when it recoils with velocity of 0.25 meter per second after firing a shell from it. Solution. Let us first write the data given. Mass of the field gun is equal to 500 kilogram. Recoil velocity is equal to 0.25 meter per second. The mass of the field gun M is 500 kilogram and the recoil velocity V is equal to 0.25 meter per second. Momentum of the gun is equal to mass M multiplied by velocity V. Momentum is equal to M into V. This is equal to 500 multiplied by 0.25. Therefore, the momentum of the field gun is 125 kilogram meters per second.
2. A car of mass of 1000 kilograms is moving with 90 kilometer per hour velocity, and a truck of 6000 kilograms is moving with 18 kilometer per hour velocity. Whose momentum is more? Solution. Given data. Mass of car M1 is equal to 1000 kilograms. Velocity of car V1 is equal to 90 kilometer per hour, which is equal to 90 into 5 divided by 18. So V1 is equal to 25 meter per second. Mass of truck M2 is equal to 6000 kilograms. Velocity of truck V2 is equal to 18 kilometer per hour, which is equal to 18 into 5 divided by 18. So V2 is equal to 5 meter per second. To find momentum of car P1 and momentum of truck P2. Momentum of car P1 is equal to M1 into V1 is equal to 1000 into 25. So P1 is equal to 25,000 kilogram meter per second. Momentum of truck P2 is equal to M2 into V2 is equal to 6000 into 5. So P2 is equal to 30,000 kilogram meter per second. Thus, though the speed of truck is very less, its momentum is more than car due to heavy mass. Three. The velocity time graph of a car of mass 1000 kilograms moving in a straight line is shown. Calculate the force acting on the car. Solution. Given data. Mass of car M is equal to 1000 kilograms. From the graph we have initial velocity U is equal to 0 meter per second. Final velocity V is equal to 20 meter per second. To find force acting on car F, the velocity time graph is a straight line. Thus, it is clear that the car moves with a constant acceleration. The acceleration A is equal to V minus U divided by T. Substituting the given values, we get A is equal to 20 minus 0 divided by 5 minus 0. That is, A is equal to 20 divided by 5, which is equal to 4 meter per second square. Let us now find out the force acting on the car. F is equal to M into A. Substituting the values, we get F is equal to 1000 into 4, which is equal to 4000 newtons. Thus, the force acting on the car is 4000 newtons. Newton's third law of motion. Having learnt about the first two laws of motion, let us now proceed to understand the third law of motion by performing an activity. Take two spring balances A and B. Attach the fixed ring of A to a wall. Connect the hook of balance A with the hook of that of balance B. Now, pull the fixed ring of balance B. What do you observe? Well, you observe that both the spring balance show the same readings on their scales. This means that the force exerted by spring balance B on the spring balance A is equal but opposite in direction to the force exerted by the balance A on the spring balance B. The force exerted by spring balance B on spring balance A is called the action, and the force exerted by spring balance A on spring balance B is called the reaction. This is an illustration of Newton's third law of motion. Newton's third law of motion states that to every action there is equal, opposite, and instantaneous reaction. According to Newton's third law of motion, when one body exerts a force on another body, the other body instantaneously exerts a force back on the first of same magnitude. These forces always occur in pairs. It is the mutual interaction between two bodies. The forces between two bodies are always equal and opposite. Let us perform another activity to verify Newton's third law of motion. To perform this activity, we require thin string, straw, balloon, plastic sellotape, and a paper clip. Fix two nails at the same height on the opposite walls of a room. Now, tie one end of thin string to one of these nails. Blow air in balloon to inflate it and carefully close its mouth with paper clip such that the balloon remains blown. Now, take piece of straw and fix it on the surface of the balloon with sellotape as shown here. Now, pass the string from straw and then tie other end of string to the nail of opposite wall such that string remains stretched and straight between both the nails of the wall. Bring the closed mouth of balloon near the wall. Now carefully remove paper clip to open the mouth of balloon. What do you notice? The balloon moves towards opposite wall. That is, the balloon moves in the opposite direction to that of escaping air. Why does this happen? Well, this happens because the equal and opposite reaction of the air coming out of the mouth of balloon pushes the balloon in the opposite direction.
Let us see some examples explaining the third law of motion. When a bat strikes a ball, the ball also exerts an equal and opposing force of reaction on the bat. The force acting on the ball projects it with high velocity. At the same time, there is a reaction force acting on the bat. This force slows down its forward motion. When a bullet is fired from a gun, a force is exerted by the gun on the bullet and, therefore, the bullet acquires high velocity. At the same time, the bullet also exerts an equal and opposite force on the gun. This causes the gun to move in the opposite direction with small velocity. The principle used for the motion of the rocket is also based on Newton's third law of motion. When the fuel in the rocket is ignited, it burns as a result of chemical reaction. The exhaust gases escape with force through a small opening at the tail end of the rocket. These gases exert an equal and opposite reaction force on the rocket. This is the reaction force which makes the rocket move in forward direction.
Let us see some more examples in our day-to-day life. A person pushes the ground backwards when he wants to jump forward. When the person pushes the ground backwards, he exerts a force of action on the ground. The reaction force offered by the ground makes him move forward. A person while swimming pushes the water backwards with his hands and feet to move in the forward direction. This is the force of action. The water also offers a force of reaction that pushes the swimmer forward. When a person jumps out from a boat, he presses the boat with his feet. This is the force of action he exerts on the boat. The boat in turn exerts a reaction force on him and pushes the person in the forward direction. This helps him get down from the boat.
In these examples, we have seen that to every action there is an equal, opposite, and instantaneous reaction. These forces act on different bodies. They don't act on the same body, hence they don't cancel each other. These forces appear in pairs. An isolated force does not exist. They also act at the same instant.
Let us now try to answer one question. Have you ever thought, why is it difficult for a fireman to hold a hose which ejects large amounts of water at a high velocity? When a fireman holds the hose, the water rushing through it in forward direction exerts a reaction force in the backward direction. The backward force decreases the stability of the fireman. Hence, it is difficult for the fireman to hold the hose pipe. Conservation of momentum.
Consider two objects, A and B, having masses m1 and m2, moving with initial velocities u1 and u2 respectively. The values of initial momentum are on m1 u1 and m2 u2 respectively. There is no other external unbalanced force acting upon these objects. When they collide with each other, the object B exerts a force F1. On the object A accelerates. Its velocity after collision becomes v1, hence the momentum changes to m1 v1. According to Newton's third law of motion, the object A also exerts an equal and opposite force on the object B. This causes a change in momentum. Suppose its velocity becomes v2 and momentum changes to m2 v2. The force F2 exerted by the object A on object B and the force F1 exerted by the object B on the object A must be equal and opposite to each other. That is, F2 is equal to minus F1. According to Newton's second law of motion, F is equal to m into A. Therefore, m2a2 is equal to minus m1a1. m2 into v2 minus u2 upon t equals to minus m1 into v1 minus u1 upon t. m2 v2 minus u2 equals to minus m1 v1 minus u1. This is equal to m2 v2 minus m2 u2 equals to minus m1 v1 plus m1 u1. Therefore, m1 v1 plus m2 v2 equals to m1 u1 plus m2 u2. Therefore, final momentum is equal to initial momentum. Hence, the final momentum of the object after collision is equal to the initial momentum before collision. Hence, the sum of the momentum of the two objects before collision is equal to the sum of the momentum of two objects after collision, provided there is no external unbalanced force acting on them. This is known as the law of conservation of momentum. Momentum is always conserved in a collision. The momentum may get redistributed among the bodies which are colliding. One body gains momentum lost by the other. Therefore, if two freely moving bodies collide, their total momentum after collision is the same as the total momentum before the collision. Let us consider an example of a bullet fired from a gun and explain the principles of conservation of momentum. Let a bullet be fired from a gun. Before the bullet is fired, both the bullet and the gun are at rest and no external force is acting on them. Hence, the total momentum of the bullet and the gun is 0. That is, initial momentum is equal to 0. Let m1 be the mass of the bullet fired from a gun of mass m2. Let the bullet acquire a velocity v1 and moves in a forward direction with momentum m1 v1. After firing the bullet, the gun moves in the backward direction as explained by Newton's third law of motion. This motion of the gun is called as recoil. Let it move with recoil velocity v2. Hence, the momentum of the gun is given by m2 v2. Hence, the total final momentum is equal to m1 v1 plus m2 v2. From the principle of conservation of momentum, we have final momentum is equal to initial momentum, or m1 v1 plus m2 v2 is equal to 0. Hence, m1 v1 is equal to minus m2 v2. Hence, the momentum of the gun and the bullet is equal in magnitude and opposite in direction. As the mass of a gun, that is m2, which is greater than the mass of the bullet, that is m1, velocity of the gun v2 is very small as compared to the velocity of the bullet v1. In a rocket propulsion, also the principle of conservation of momentum is followed. Rockets expel burnt fuel in the backward direction with a very high velocity which pushes the rocket in forward direction. So momentum of the rocket and the fuel are equal in magnitude and opposite in direction. Fuel is expelled with very high speed. Therefore, sufficient momentum is acquired by the rocket in the forward motion.
Let us now perform an activity. We require a test tube of good quality glass material, a stopcock, 2 wires, and water. Take a small amount of water in the test tube. Place the cork at the mouth of test tube. Suspend the test tube with the help of 2 wires. Now, heat the test tube until water vaporizes. Continue heating the test tube until the cork blows out. What do you observe? You observe that the test tube recoils in the direction opposite to the direction of the cork. It is also noticed that the velocity of the cork is greater than the recoil velocity of test tube. Why is it so? Well, the velocity of cork is greater than the recoil velocity of test tube because there is a difference between the mass of test tube and the mass of cork. That is, the mass of test tube is greater than the mass of cork. Thus, the momentum of test tube is equal to the momentum of cork. Let us solve some numerical problems on what we have learned.
1. A railway wagon of mass 2500 kg moving with a velocity of 36 km per hour has a head-on collision with a stationary wagon of mass 3000 kg. If the two wagons move together after collision, calculate their common velocity after collision. Solution. Let us first write the data given in proper units. Given M1 is the mass of the moving wagon given as 2500 kilograms. M2 is the mass of the stationary wagon given as 3000 kilograms. The initial velocity of the moving wagon is U1, which is 36 kilometers per hour. Let us convert this into SI system. This is equal to 36 into 1000 meters divided by 60 into 60 seconds, which is equal to 10 meter per second. The initial velocity of the stationary wagon is U2, which is equal to 0 meter per second. Let us find the common velocity v, which is equal to v1 equal to v2. By the law of conservation of momentum, m1u1 plus m2u2 equals to m1v1 plus m2v2. Substituting values, 2500 multiplied by 10 plus 3000 multiplied by 0 equals to 2500 multiplied by v plus 3000 multiplied by v, or 25,000 plus 0 equals to 5500 into v. Therefore, v is equal to 25,000 upon 5500. Therefore, v is equal to 4.545 meter per second. Therefore, v, that is, the common velocity of the two wagons after collision, equals to 4.545 meter per second. 2. Two balls of masses 50 grams and 100 grams are moving along the same direction with velocities 3 meters per second and 1.5 meters per second respectively. They collide, and after the collision, the first ball moves with the velocity 2.5 meter per second. Determine velocity of the second ball. Solution. Let us first write the data given in proper units. Given mass of the ball m1 is equal to 50 gram is equal to 0.050 kg. Mass of the second ball m2 is equal to 100 grams, which is equal to 0.100 kg. Initial velocity of the first ball is equal to u1, which is equal to 3 meter per second. Initial velocity of the second ball, u2, is equal to 1.5 meter per second. Final velocity of the first ball is equal to v1 is equal to 2.5 meter per second. Final velocity of the second ball, v2, is what? By the law of conservation of momentum, the total initial momentum is equal to total final momentum. m1u1 plus m2u2 is equal to m1v1 plus m2v2. Substituting the values given, 0.050 into 3 plus 0.100 multiplied by 1.5 equals to 0.050 into 2.5 plus 0.100 into V2. Therefore, 0.150 plus 0.1500 is equal to 0.1250 plus 0.100 into V2. 0.3 is equal to 0.125 plus 0.1 into V2. We have to find the final velocity of the second ball, that is V2. 0.1 into V2 is equal to 0.3 minus 0.125. V2 is equal to 0.3 minus 0.125 divided by 0.1. V2 is equal to 0.175 divided by 0.1. V2 is equal to 1.75 meter per second. Therefore, V2, that is the velocity of the second ball after collision, equals to 1.75 meters per second.
3. From a rifle of mass 4 kilograms, a bullet of mass 50 grams is fired with a velocity of 35 meter per second. Calculate the recoil velocity of the rifle. Solution. Given data. Mass of rifle is equal to 4 kilograms. Mass of bullet is equal to 50 grams, which is equal to 0.05 kilogram. Velocity of bullet is equal to 35 meter per second. To find the recoil velocity of rifle, initially, that is, before the bullet is fired from the rifle, the bullet and the rifle are at rest. Thus, the initial velocity of the bullet and the rifle is 0. So, the initial momentum of the bullet and the rifle is 0. Let us now substitute the given values in the relation. Mass of bullet into velocity of bullet plus mass of rifle into recoil velocity of rifle is equal to 0. We get 0.05 into 35 plus 4 into recoil velocity of rifle is equal to 0. 1.75 plus 4 into recoil velocity of rifle is equal to 0. Recoil velocity of rifle is equal to minus 1.75 divided by 4. So, recoil velocity of rifle is equal to minus 0.4375 meter per second.
The negative sign indicates that
The rifle recoils
backwards